So we are continuing to talk about surfaces. Okay, and we're going to talk about stress, corrosion, and stress and corrosion and cyclic stress. The main thing is if we have an applied constant stress in a corrosive environment, then that equals bad, and it equals failure at lower stresses than you might expect. And if we have corrosion and cyclical stress, we have a further reduced fatigue life. So even if we go through all of the work to identify the stresses properly, we find all the stresses and they're all correct and accurate, but then we put those same stresses in a corrosive environment, then we actually don't know exactly what the stress that causes failure will be, but we do know that it's reduced. Same thing for fatigue. If we find our fatigue life due to loading conditions, even with our surface factors, but then we add corrosion to the fatigue, then we actually have a fatigue failure at a reduced life. So in both cases, the stress corrosion and cyclical stress lead to reduced life of a component. It's different behavior when we treat the stress and corrosion separately. So if we just look at corrosion and we look at the surfaces, or we just look at the static stresses or dynamic stresses, we can't really say that the net effect of these is not equal to the corrosive effect and the loading conditions. Sorry about this. Loading conditions. Okay, so the net effect is not equal to the sum of the independent effects. So what we have to do is we have to really just kind of get some ballpark numbers for what that is. Alright, so sorry this is painful. Hopefully it'll get better as time goes on. For example, some stainless steels, and that's my Doberman. She's very loud. So some stainless steels don't experience corrosion unless there is some applied load or stress. And the reason I said or stress, because we could have could be residual stresses. Okay, and in particular, tensile residual stresses is always bad. I'm really sorry about that. So tensile residual stress is always bad when combined with corrosion. Okay, All right. So corrosion, and particularly what we're looking at is stress corrosion. It's always associated with tensile loads. Okay, and it might be intuitive that we have some object, okay, and then this object is subject some tensile load, and we get some funk on the surface due to corrosion. Then the corroded surface, if we take a closer look at it, then the corroded surface will have our nominal surface, and then we have the corrosive effects, and those corrosive effects can cause cracking. So if we have a crack that starts to form and we have tensile stress due to some applied or residual load, then it'll cause this crack to propagate a lot faster through the material. So when we talk about stress corrosion, we're talking about the corrosion that's due to crack growth in the presence of a corrosive environment and an applied load. And we said in the last lecture that corrosion is a mechanism that's either chemical or electrochemical, and often it involves metal ions leaving the surface. For aluminums, that'll react with oxygen to form an oxide layer, but for some iron materials, this actually results in flaking of the material, which flakes off in the form of iron oxide or rust. When we have the stress corrosion, so stress corrosion, cracking occurs on the order of 50 to 75% of the tensile yield strength, which is pretty remarkable, and so that's why it's extremely important for us to consider stress corrosion effects on materials. Turns out that things like shot peening and other surface treatments can help dramatically. Sorry about this, I keep fat fingering the scroll. Alright, so there's some basic design guidelines, and that's really the big picture of it, and that is when you have materials that corrode, or you have materials in a corrosive environment, you really got to do something. Alright, so there are some design guidelines for stress corrosion, or when you expect corrosion to occur. There's a few things you can do. Number one is you can change the material to a less reactive material in that environment. You can introduce cathodic or cathodic protection in the form of coatings dielectric shielding or making the environment less corrosive. Okay. The third thing you can do is reduce the tensile stresses. Okay. This can be done by reducing interference fits. Okay, so often you'll see corrosion that occurs on tight fitting interfaces that produce tensile stresses. You can use more material. Okay. For example, you have material that experiences load. Well, distribute the stress through this cross section. Then by adding a little bit more material, then that load is distributed over a larger area, reducing the tensile load. You can also anneal the material, or you can do shock heating of the surface. When we anneal the material, we basically just heat it up and allow the stresses, internal stresses, to relax. The only caveat is when you anneal a material, you actually are making it less hard and more ductile, and we know that the resistance to fatigue is actually improved by having harder materials. So there's likely a trade-off there that you need to be aware of. So we can take a look at how certain materials behave in different corrosive environments, and this is a chart from your book, and what it shows is it shows the material in the center and the corrosive environment around the ring, and it ranks the resistance of corrosion from A to D. So materials that are in the A category have good corrosive resistance to that environment. So for example, if we wanted to take a look at the resistance of Teflon, we can see that Teflon performs really well in salt water. Teflon also performs well when there's strong acids, and it also performs well strong acids. It also does well in strong bases, alkalis. It also does well with organic solvents, and it doesn't do as well for UV radiation. And so this is a quick way for us to kind of look at how well a material performs. You can see Teflon actually shows up in the outer ring for most environments. If you looked at alloys, though, all alloys don't do well in organic solvents, and they don't. And different alloys perform different ways in acids, and so basically you can use this chart to take a look at if you're considering using a material or you are you know that your material is going to be in some environment. So say for example around the ocean in salt water, or in the north where the roads are salted. If you're designing something, you would want to consider which material you put in that environment. Okay, and so the different materials will behave different in different environments. And if we look at the cyclic stress, if we look at the cyclic stress and corrosion, we see what we saw earlier, and that is that the fatigue life is reduced considerably. And unfortunately, we don't really know how much the life is reduced. Okay, for general cases. So what that means is that if it's important, then we have to do engineering tests to validate the design. Sorry. For that particular environment. And there's testing companies and testing services, and they will test your product for you or your device for you. Or there's guidelines for different environments and different tests that you can do to see how a material will do. One of the things that is important to note is that corrosion fatigue, as this is called, when you have cyclical stress and corrosion, it's called corrosion fatigue. Corrosion fatigue doesn't just depend on the number of cycles in the cyclical load of loading. Okay, it also heavily depends on time. Now, if you have a constant frequency, obviously those two, if you have a constant cyclical load, over time, then obviously there's a relationship between, the number of cycles and time. But if you don't necessarily have constantly fluctuating load over time, but you do kind of expect a certain number of cycles, and you expect a certain duration that your design or your artifact is out in that corrosive environment, then the overall life is really going to depend on both. Okay, so the overall life, is going to depend not only on the stress amplitude and cycles, but also how long. Goodness gracious, my apologies. We'll get this together. But also how long the material was exposed to that environment. Okay, so in general, the fatigue strengths and tensile strengths for corrosion fatigue are not correlated. Okay, so this is a huge caveat when you have corrosion. So this is one point. Another point is that alloy steels typically have a higher corrosion resistance. Okay, and residual tensile stresses, as we've said earlier, are always bad. And they will negatively affect or reduce the fatigue life further in a corrosive environment. Okay, so you'll want to protect that. Okay, the next type of surface wear that we're going to consider is actually cavitation. Okay. Okay. So cavitation is the formation of cavities or bubbles due to pressure gradients caused by a relative velocity between a component and a fluid. Okay. Bubbles form due to this pressure difference and also collapse due to pressure gradients. Okay. When the bubbles collapse, it can cause high pressure waves to damage, excuse me, the surface. In fact, there's enough pressure to cause plastic deformation in metals. Which is pretty remarkable when you think about it. Okay, this is a common problem in, I will say, pump applications, and that would include centrifugal pumps, impellers, turbine blades, and others. So what this looks like is actually pretty interesting. So these are some pictures that were taken from Wikipedia on the web of a gear pump, and there's actually a video that you can watch. But this is gear pumps. This is 2 gears. This is a lubricating oil. So as they spin, you have high relative velocity between the fluid, which is stationary down here, mostly stationary, and the actual gear teeth. And as they spin up, it can cause bubbles to form because of the pressure differences. It's almost kind of like creating a vacuum, so a bubble will form. And then if the bubbles form, when they pop on the surface, it actually causes a large pressure gradients. This is another example of an impeller, how the bubbles will form on the surface due to this pressure gradient. And then when they pop, they'll actually cause these high stresses to actually shoot down to the surface, which causes the damage. And the damage that's caused is actually pretty remarkable. So this is what the cavitation damage can look like. You see the damage here to the surface and the damage here as well. Okay. This is another graphic that just shows a different picture. This is from slurry flow, and it shows how if a bubble forms, then when it collapses, it actually creates this microjet, this type of supersonic fluid microjet that attacks the surface. So that's what's going on here, and you can see how the bubbles are forming on the surface. And so that's cavitation. Okay, so that covers the stress corrosion, cyclical corrosion, and the cavitation concepts that you need to be aware of when it